today we will take the topic called alkenes. Alkenes are unsaturated aliphatic hydrocarbons with carbon-carbon double bond as a functional group. This functional group, whenever they have, this is C double bond C, they are called double bond functional group, they are called alkenes. However, they must be prepared, that is constituted by only the hydrogen and carbon only. Aliphatic means open chain, there is no rings, aromatic type. Unsaturated means either double bond or triple bond. Under the category double bonds are called alkenes. If a triple bond is there, obviously they are called alkynes. But let us take alkenes today. The smallest example of this category is with two carbons we have first member called systematically they are called alk ene plus E. So, two carbons are there, eth plus ene. This is IUPAC name in fact, regular name or systematic name. Eth stands for two carbons, En for the functional group. There is no other functional group, therefore E is there. And the common names also there for some compounds, like this compound also it is known as ethylene. This name has come much prior to the IUPAC system. So, old names are still, it is in practice, ethylene is the common name. If the compound is slightly little bit bigger than this one, then with three carbons, this is known as propene. Three carbons, so therefore propene, propene. Commonly you can call it as a propylene, or it is also known as ethylene plus one methyl extra. So, we call methyl ethylene. Methyl ethylene is also one of the common name for the compound. That is ethylene, you know it up to this is ethylene, this is extra. So, this is one of the common method by having a substitution in the place of hydrogen methyl. So, the methyl you tell and then say ethylene, methyl ethylene. Like that a compound may be said, for example, if compound is like this center part is ethylene, all these four methyls are extra groups, so CH3, 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 CH3. In such a case, the system you have to say butene containing a double bond in the center, therefore it is called a 2-butene with the two groups extra. So, one is at second, one is at third carbon. So, you call it as a 2,3-dimethyl, 2,3-dimethyl 2-butene, or you may call it as a commonly, this middle part is ethylene, all the four are methyls. So, you may call a common name as a tetramethyl ethylene. So, all alkenes you can name by ethylene nomenclature. Say ethylene, all extra groups one after the one you say, and then say ethylene. It is a common method, but systematic name is you have to select the longest chain and identify the double bond position and say 2-butene, 4 and so on. Number you have to say, then say alkene, and what all extra is not covered in the main chain will be said as a prefixes, and then finish the. So, let us go some preparation methods. There are two fundamental methods are there for the preparations of double bond we are preparing, right. So, double bond can be prepared from the single bonded compounds, or can be from triple bond you convert into double bond, or single bond may be converted into double. So, there are two fundamental procedures. One is by converting triple bond into double bond, Another one is from double bond. If you remove the A and B groups, these groups if you delete, you will get this. These procedures are called elimination methods. Elimination methods. Whereas by converting triple bond into double bond is called addition methods. So fundamentally there are two methods are there. One is addition method, the other one is elimination method. Finally, our goal is to create a double bond in the given compound. So first let us go for this addition methods and then we will take this elimination methods. So let us take first the preparation methods. In this, as I said, first method is by converting triple bond into the double bond. These methods are called addition methods. In this methods, a simple method you may quote it that add hydrogen to the acetylene, you will get ethylene. But reaction takes place twice, you will get ethane. So therefore, the addition of hydrogen should be restricted, or in a selective method you have to say. That is one such method is a partial reduction, in fact. Partial reduction. The reduction using the, let us take acetylene, add hydrogen gas, but don't use the nickel catalyst. If you use nickel catalyst, once it is added, once again the hydrogen will be added. Instead, you take the palladium catalyst over barium sulfate, and an organic compound quinoline is used as a solvent. Both this sulfur present in the barium sulfate and the quinoline will control the addition of hydrogenation to some extent, and then therefore only one step of addition takes place, you will get double bonded compound, that is all. On this, even if you continue the reaction for some more time also, reaction will not take place, though you add hydrogen and the same condition. But if hydrogen nickel is added, you will get again ethane formation. So to stop at the level of the acetylene is converted thereby into ethylene or ethene. So to prepare ethene, this particular the combination, what is that? A catalyst palladium supported by the barium sulfate in presence of quinoline. This particular the catalyst using this palladium and all that is introduced by a scientist called Lindlar. So therefore this is also known as Lindlar's catalyst. Instead of this type of the catalyst, we have another method. The acetylene is taken in the another method, treated with the sodium and liquid ammonia. Ammonia is originally a gas, but this gas should be cooled enough so that liquid is formed, or under pressure also the ammonia can be converted into the liquid. You have a liquor ammonia in the market, that is ammonia gas dissolved in water. This is liquid ammonia. Ammonia really it is cooled or compressed to get the liquid ammonia. That liquid ammonia and the sodium together is working as a reagent to reduce. In this case also you will get this CH2 double bond CH2. So it is also a partial reduction taking place and you will get the ethylene. However, if you take acetylene and add hydrogen nickel, you will get ethylene and again reduction takes place, you will get ethane. So if we are interested in the preparation of alkanes, no doubt acetylene is added with hydrogen and nickel catalyst so that ethane is formed. But in both these two cases, the reduction is controlled or partial reduction or a selective type of the reduction. In these reductions, you are getting only up to alkene. Here we have one specification also. If the compound is a butane, if the compound is butane, and treated with the first reagent, what is that? Lin-Lar's catalyst, palladium, barium sulfate and quinoline. You are getting double bond, but the two methyls goes to the same side. The first method, you get this type of specific compound, it is known as cis 2-butene. Whereas the same compound, if you do the second type of, that is sodium and the liquid ammonia, this type of reduction will give the butene, but the two methyls are opposite, that is called a trans 2-butene. So both are different now. This is a trans 2-butene. So in the first case 2-butene, and in the second case trans 2-butene, but it is in the trans type. So how you are able to get this type of the two different types of the butenes? Just using the different reagents. Starting material is same 2-butyne, but we have taken is 2-butyne, we have taken ine, we have taken enes, we are able to get, and it's also selective reduction. But the reaction has another specification. What is that? Stereochemically we are able to control barium sulfate, palladium, it is added. The stereochemistry is also controlled type. How it is explained means, let us see a small mechanism or reason for the getting cis and the trans. In the first type of reduction, the mechanism for the cis type of formation, a butane, if it is represented like, it is a linear molecule, straight chain structure, because middle carbons are sp hybridization, and this molecule and the hydrogen gas both are adsorbed on a palladium particle. This particle, it is not atom. The square I have shown is a piece of palladium, on which the gas 2-butene is a gas, hydrogen is also a gas, both are going and settling on this solid the palladium. It is a solid piece. This type of settling on the solid particle is called technically adsorption. Adsorption is a physical phenomena which is not there is no chemical bond formation between the palladium particle and the alkyne or hydrogen, just physically, just because of the van der Waals forces they stick to this. So whenever van der Waals forces are developed, some attraction, stabilization taking place. So the molecules both side by side they adsorb. The chance is there, then only adsorb in fact. But after attacking this is there will be a slow rapport takes place. Because of the proximity, the hydrogens may have a slow bond develop between the C and the H, and the old bond between the H and H and the C and H, one of the pi bond is opening, and you can find a 4-membered ring formation, and slowly as the hydrogens are making bond formation more and more becoming strong, and the old bond becomes weak and weak, and then this totally disappear, and this system changes into another like this. A double bonded carbons are attached with the hydrogens and the carbon. Because of the hydrogen is as a molecule has come, both the hydrogens will come one sidedly. So finally, in order to maintain the angles, the 2-butene will have a 2-methyl same side and the hydrogens will be on the opposite side. Okay. The geometry will be a trigonal planar at each carbon. So in order to maintain that, the carbons will be slightly adjusted other side and the hydrogens will be adjusted this side. This is exclusively cis compound. Whereas the same compound, if it is treated with sodium and ammonia, this is the mechanism for the first method, right? Another mechanism for the second type of the mechanism. In this reaction, what is happening? First, sodium, when it is reacting with ammonia, sodium loses one electron, and these electrons are surrounded by the ammonia liquid. Huge number of ammonia molecules will be encircling the electron. This is called a solvated electrons. This situation shows a blue coloration. In the inorganic chemistry, you find this property. Alkali metals, when added to the liquid ammonia, solution becomes blue. What is happening is this free electrons are available. Sodium gives out electron and becomes into a Na plus. So, one electron come out, because when compared with the atomic stage of the sodium, when ionic electronic configuration, ion electronic configuration is stable. So, therefore, readily it dissociates, provided somebody should take electron. That is why when the presence of ammonia, it is possible to lose the electron, and the electrons are solvent encircle and makes a solvated electrons. If time is given, what happens? Ammonia gives a proton, that proton takes electron. But before that happens, you immediately add this the alkyne. So, this alkyne takes these electrons now, pass the alkyne into this blue colored solution. So, the electrons are, the pi bond opens and one electron is added this side, another electron, take 2 sodium and 2 electrons and 2 sodium, another electron you add it to the other side. Okay. So, each side one electron is added. By opening the pi bond, you get 1 electron. By adding 1 electron, 2 electrons are formed. So, this gives into a system where, so we have a triple bond has become double bond, but this side 2 electrons, the other side also 2 electrons are formed. Now, when 2 electrons are, clouds are side by side, there is some repulsion because of the negative charge. So, this electron repulsion leads to give the reorientation of this structure, because it is cloud. So, cloud can diffuse. So, we can call it as a reorientation. There is no much change in the structure, but the cloud, one of the cloud will come from upside to downside. So, you get a molecule like this. The one cloud will be there only, but one cloud will come opposite side, so that a repulsion is avoided. Now, consequently, the methyls also, they will take a opposite direction in order to adjust this electron clouds. Now, we are adding the protons. Where from these protons will come? The ammonia, by the time ammonia will split up now into proton and the NH2 minus. This is what ionization of the ammonia into proton and the NH2 minus. I am sorry, this is minus. So, amide anion and proton. If nothing is available, this medium, proton and electron will join, hydrogen atom is formed, they too join hydrogen gas and come out. But already we have passed alkyne, therefore, electrons will add first. Then afterwards, the protons are added. These protons are, take 2 ammonia, you will get 2 protons. Each side 1 proton you add. So, take 2 protons, one added on this cloud and another added on another side cloud. So, therefore, 2 protons are added each side, and the compound now becomes into a 2 hydrogens, one on the right side, one on the left side. So, 2 methyls, when you compare the position of the methyls are occupying the opposite position, hydrogens are occupying the opposite position. In the first time, what we have added, the whole molecule is added. That is called molecular addition. In this case, we are adding first electronation. Electron addition is a reduction, in fact. So, first electrons are added, then followed by protons. So, electronation followed by the protonation. After electronation, because of the repulsion, they are reorienting and the protons are added. So, consequently, what you will get is a trans compound you are getting. There may be a small minor product may be formed in this process trans and in this process cis, but major compounds almost to a high percentage. When you add this Lindlar's catalyst, exclusively cis to butene is formed and sodium liquid ammonia is added. almost exclusively trans butene is formed, right. So, both are converting the triple bond into the double bond, and that too selectively, that is partially reduction. If total reduction is there, alkanes will be formed. So, any compound you can take acetylene, you can take propyne, you can take, but if the groups are there, specifically cis and trans type of alkenes are formed. This is what the first method, that is addition method, right. So, then let us go for the second method, that is elimination techniques. So, let us go for the second method, that is elimination method, that is taking single bond and dropping this A and B groups selectively and to prepare a double bond. These methods are called elimination methods. Elimination methods. In these methods, the methods are again subdivided into what is that AB you are removing. If AB is 2, 1 hydrogen, 1 halogen, it is called dehydrohalogenation. If water is removed, dehydration. If halogens are removed, dehalogenation, and so on. Okay. So, based on the what is AB, the elimination methods can be subclassified into the ABCD. First, let us take 1 H and 1 halogen. This is called as a dehydrohalogenation. Actually, it is dehalogenation, but refer for the both dehydrohalogenation. So, removal of the 1 hydrogen, 1 halogen from side by side carbons, you will get the double bond. So, let us take one example, CH3 CH2Cl. So, from this side Cl will go, from this side 1 hydrogen is going out. So, as the HCl is removed, and then you get the CH2 double bond CH2. Now, you can guess what type of reagent will work out. This what we are removing is HCl is an acid, isn't it, that you know. So, acid you want to remove from the compound means a strong base must be used. That is the guessing. In fact, it is the alcohol dissolved. It is called alcoholic potassium hydroxide works for this function. So, alcoholic KOH removes HCl. This HCl react with the KOH, forms into KCl and water. So, it is a balanced equation now. Ethyl chloride plus KOH gives ethylene, KCl and water. So, what is removed is HCl. So, therefore, I call this process as a dehydrohalogenation, right. So, but this removal instead of HCl, you can also remove the 2 halogens also, that is called what dehalogenation. Minus of X2 is known as dehalogenation. 2 halogens. If system is having the 2 halogens side by side, then the 2 halogens can be removed. Like for example, 1,2-dichloroethane is there. You add zinc powder. This is a liquid. Dichloroethane is a liquid. To this liquid, add some zinc powder and then boil for some time. Zinc takes away these 2 halogens and forms into zinc chloride is formed. ZnCl2 is formed, and the 2 carbons now will get a double bond in between the carbons. You will get ethylene formation is taking place. So, 2 halogens I am removing, therefore, I call it as a dehalogenation. But which compound should be dehalogenated means 2 halogens should be side by side. If only 1 halogen is there, I want to do this reaction means it is not possible. So, the taken compound should have a halogen, the 2 and side by side you must have, not on the same carbon. So, side by side if 2 halogen, the type of compounds are called 1,2-dihalo, or you can also call they are called vicinal. Vicinal or vis dihalo compounds. 1,2-dihalo systems also called vis or vicinal dihalo compounds only allowed. If 1,1 is taken, you will get joining type of reaction and you will get 2 butene in clubbed manner. For example, if two halogens are like this, you take a zinc, just like Wood's reaction, extension reaction it is. If one more compound is written like this, two zincs will take away this, and the reaction is coupled, and compound will become two butene, double compound is formed. This you cannot call it as a dehalogenation or elimination reaction, because two molecules join, that is called a coupling reaction. Actually, the total concept of the elimination concept, it won't be covered. So therefore, the halogens should be side by side, then removal of the two halogens and construction of double bond taking place. If one H and one OH, that is HOH, or you can call it as a minus of a H2O, this is called what? A dehydration. So for to do the dehydration, one OH function should be there. So a compound like this CH3 CH2OH, this from one side OH, the other side hydrogen is removed, and you will get ethylene formation. So I am removing the water. So what may be the reagent? You can guess water removal generally from the concentrated sulfuric acid, and that too at a little higher temperature, because removal of water always the favored by the higher temperature, because water comes and evaporates. So as the water is going out, forward reaction will be going on, taking place. So therefore here the temperature is around more than 140 or 170 degrees centigrade, and the reagent is concentrated H2SO4. So concentrated sulfuric acid heating at 170 degrees, the water will be removed, and you are getting a alkene, corresponding alkene. If you take ethanol, you will get ethylene. This water will be evaporated and removed as a steam. So water will be the byproduct in this reaction. It is a reversible reaction. If you don't remove the water, if you cool it, again water adds and you will get ethanol. So therefore, the moment reaction takes place, the water should be removed from the system, so that alkene will be the form. So all this A, B, C are removing certain groups. Therefore, I called it as a dehydrohalogenation, dehalogenation, dehydration. Similarly, we have some more the elimination techniques. Minus of CO2. This method is called what? A decarboxylation. Removal of CO2 is called decarboxylation. A compound containing two COOHs side by side can be dropped out. This is called succinic acid. Okay, this succinic acid, in terms of sodium salt, you take both the sides, you take sodium, that is called disodium succinate. Disodium succinate, saturated acid it is, and add some water, do the electrolysis. So here CO2 will go minus, actually COO minus, lose one electron, becomes free radical. The CO2 will go, dot will come here. Similarly, COO minus will become dot, and then decomposes into CO2, a dot is formed. Two free radicals will join up, and you will get ethylene formation. A double bond is formed. This is a Kolbe identified this reaction, so it is called Kolbe electrolysis. Both the carbon dioxide will come as two carbon dioxides, and the Na and OH forms NaOH. From water, OH will come, two hydrogens will be liberated as a hydrogen gas. So the alkene and the CO2 is released at anode. In the electrolysis, we use the metal rods as an anode and cathode. So alkene and CO2 is released at anode, sodium hydroxide and hydrogen is released at the cathode. So this is an extension to the, in the alkanes we have used this Kolbe electrolysis, this is known as. So the same reaction, only thing is there it is separate units, that is sodium acetate, two were joined, ethane formed. Now, already single bond is there, a double bond probably. If double bond is there, definitely the method is extendable for the preparation of triple bonds even. Same method we will see in the alkynes preparation. So, the Kolbe electrolysis of disodium succinic acid, dicarboxylate it is. So, disodium succinate on Kolbe electrolysis, we are getting this ethylene formation. This is also one of the elimination reaction. And lastly, we have one more elimination. This reaction is a sort of in a alkyl group, if it is attached to a nitrogen in 4 times. This is called what? 1 R is attached, it is called 1 degree amine. 4 are attached. 3 attached 3 degree, it is 4 are attached, therefore N will acquire the 4th degree, a positive charge. Quaternary amine hydroxide you take and then heat it strongly. This is called pyrolysis. Pyrolysis means pyro means temperature, nolysis means cutting of the bond. Pyrolysis, nolysis. So, pyrolysis means applying the temperature, we are breaking the compound, that is without any catalyst or so. Pyrolysis means merry heating makes the compound to break into pieces, that is the definition for pyrolysis. So, the compound out of the 4 groups, 1 group becomes into ethylene. Remaining 3 goes with the N only. With the N, now you are getting the 3 ethyl groups, right? A neutral tertiary amine, that is triethyl amine, will be detached. Out of the 4 groups, 1 group undergoes D, that is the amino group, and the hydrogen is dropped, or H and OH is dropped, otherwise you will get a removal of water. So, out of the 4 groups, 1 group becomes into alkene. So, it is also an elimination reaction, but fundamentally the last one will not follow the symptoms of ABC. The A, B, C, D are following the general rules of elimination, that is Sedgwick rule they follow, but this follows a anti-Sedgwick rule, that when we take little extension to this, the features of elimination all together, because we have taken a simple example, ethyl chloride and dichloroethane, smaller the molecules we have taken, but if the compound is a little big, then how the elimination takes place may be discussed after this the preparation. So, there are 5 eliminations are there: dehydrohalogenation, dehalogenation, dehydration, decarboxylation, or pyrolysis of quaternary ammonium hydroxide. These are all solids. It is a salt, N plus with OH minus. The salt is heated so that tertiary amine and 1 alkene and 1 water is formed. So, pyrolysis of quaternary ammonium hydroxides is also under one elimination reaction we are taking. So, under the preparation method, as I said, the elimination method specially, when you are applying this elimination reaction, the reaction has some features, little difficulty. If a bigger alkene is taken, what happens? So, these are all under one statement called the features of elimination reaction. Features of elimination reaction. The elimination follows the elimination follows or elimination prefers otherwise beta elimination. That is, for example, if I have a halogen I am removing, but the hydrogen may come from this side may come from this side. Which side the hydrogen coming? Because that side we have hydrogen, this side. In the previous case, if it is a ethyl chloride, H and Cl is fixed. So, therefore, HCl will go, ethylene will come. But now this Cl is going out, it can take the hydrogen from the either from this side or from this side. Under this case, we have some more hydrogens, isn't it? So, now with reference to the halogen, this carbon is called alpha, and even alpha also we have a hydrogen, right. So, whether this hydrogen or the side by hydrogen means it always prefers a side by hydrogen only, this side or that side hydrogen will be taken. So, not this particular hydrogen, these two are called beta hydrogens. So, one of the either this side or that side beta hydrogen will be taken. So, you get the two types of the answers. So, if that side hydrogen is taken, it is a right side beta. If this side left side beta will be removed. But never this hydrogen is removed, because if this hydrogen is removed, you get a carbene formation. So, therefore, these both are beta hydrogens removal. Alpha hydrogen is removed, then we will get a carbene formation, that is a lone pair and a vacant orbital, a carbene is formed, which is a alpha type of the elimination. Generally, this will never takes place, always favors the beta elimination. Either that side or this side takes place. Beta carbon hydrogen only will be removed. Beta carbon hydrogen is called beta hydrogen. Alpha carbon hydrogen is alpha. Alpha hydrogen removal leads to destabilization of the product, whereas beta hydrogen, if it is removed. After this, we have another point. We have two different beta hydrogens are there. Then out of these two, which is more stable, means there comes a rule called Sergev rule. The rule says that whenever we have two beta hydrogens, the beta hydrogen you remove in such a way that the alkene will have the more number of alkyl groups. This is one way. This alkyl has only one alkyl, two alkyl. This is called dialkyl alkene. This is called monoalkyl alkene. So, the rule is in one way it is defined. Whenever HX is removed, you will get a alkene having the more alkyl groups. This is one way definition. Or if Cl is taking, this is the only Cl, but which hydrogen? Here the hydrogen has 3 hydrogen, here hydrogens 2 are there. So, therefore, H comes from, you can also define like this, H comes from a beta carbon with a less number of hydrogens, So, this side 3 hydrogens, this is beta, this side 3, this side 2. So, 2 is less number, so therefore, less hydrogen side comes. So, 2 butene will be the major answer. So, this is what identified by a scientist called Sergev. This rule is defined as Sergev rule. Whenever alpha, beta available, always beta hydrogen goes. If 2 betas are different types of betas are available, second rule says, that is called Sergev rule says, out of the available different beta hydrogens, one of the beta hydrogen where the number of hydrogens are less, here 2 and here 3. So, 2 sides beta hydrogen, that gives this. This is all why it becomes like that, why only the hydrogen comes from the a beta carbon with less number of hydrogens means if beta hydrogen, if it is removed, you will get a 2-butene which is having a 3 plus 3 6 hyperconjugations, 6 hyperconjugable hydrogen, that time 3. This side has got only, these are the immediate unsaturated, immediate saturated hydrogens, only 2 are there, 2 hyperconjugable hydrogen. So, this preferential type of elimination is in accordance with the stability of the product. So, 2-butene is having 6 hyperconjugable hydrogens, each hydrogen shows a phenomenon called hyperconjugation similar to the resonance. So 6 times it is stabilized, whereas this is only 2 times. That is why the 2-butene will be the major product over a 1-butene, a minor. This is also will be formed, but a minor product will be coming. So major product is 2-butene. The minor product will be the 1-butene. So both will be formed. Why 2-butene becomes means as a whole, you can say it is in accordance with the Sergev rule. What makes the background for this discussion means the product 6 hyperconjugable hydrogens, that is the reason we are getting that one as a 2-butene as a major product. This is what Sergev rule, right. The rule is applicable for the not only dehydrohalogenation, dehydration and so on also. Whenever HX is removed, the X is fixed, but H comes from the carbon where hydrogens are less in number. You can also find a brief mechanism of HX removal. Let us see dehydrohalogenation, how it exactly the elimination mechanism is operating means there can be 2 fundamental differences. The first one is E2 elimination. In the E2 elimination, the H and the halogen simultaneously going out because of the influence of the KOH. The OH minus will take the hydrogen and leave the 2 hydrogens and these 2 electrons to the system, and the chlorine withdraw 2 electrons. All this, the OH taking hydrogen, 2 electrons shifting B, and this shifting all this A, B, C smaller this part of the reactions. Let us say OH taking the proton, 2 electrons shifting B, 2 electrons shifting C. This A, B, C will synchronize at a time, and therefore it is only single step reaction. So only one step is involved in the reaction, double bond will be formed. So naturally this is the only one step, so rate of the reaction depend on the both alkyl halide concentration as well as the concentration of the base also. So both the concentration, either one concentration you increase, rate increases, you decrease, rate decreases. That is why it is called E2 elimination. 2 stands for the bimolecular elimination. Elimination bimolecular. So elimination goes through the bimolecular elimination if H and Cl simultaneously goes out. There is another type of elimination, E1, whenever the H and Cl you are removing. If the Cl attached carbon has so many alkyl groups like this, it is a 3-degree alkyl halide, and even the hydrogen attached carbon also, if so many alkyls are there, it is a 3-degree carbon. In such a case, though you have taken KOH and you are heating, the OH coming and taking proton may not be taking place readily because of the big groups are obstructing a stereo. Chemically, the not possibility will be the criteria. So therefore OH obstructing proton is not taking place initially. Then the reaction should not take place, but it is found that the reaction is taking place because of all these alkyl groups are electron withdrawing donating groups, and thereby they will put a pressure of this electron density push up will be there. So the halogens feel now outgoing property or the leaving capacity of the Cl will be increased. So before the H going out, first Cl will go out. So it takes place in the stepwise manner. Therefore in the step 1, first Cl will be departing or leaving. So this is called minus of Cl minus. So you get a carbon as a carbocation is formed. The moment carbon becomes carbocation, the symmetry of the carbon will be totally changed. So this will become now a trigonal planar carbon. Once the Cl takes electrons and goes out as a Cl minus, this becomes a trigonal planar. However, the stereochemistry problem will be there in the still on the second carbon, because it is 3-dimensional carbon with a tetrahedral symmetry. But the OH can come now from the side of this carbocation and reach the proton, or from the back side of this trigonal planar can reach the proton. Either way it can come and obstruct the proton, and immediately the 2 electrons will come and a double bond is formed. So, second step happens to be a little better step than the first one. So, therefore, considerably step 1 will be the slow step. In this slow step, what OH is doing means nothing. It is waiting till the Cl goes out. Once the Cl goes out, because here the big groups and here the big groups are hindering. So, the OH cannot come either from the front side or from the back side. So, until the Cl goes out, the OH cannot do anything. So, the addition of OH little more concentration or less concentration will not alter the rate of the reaction. So, rate depends only on the alkyl halide. First alkyl halide, if it becomes a carbocation, then the second step is a fast. So, the OH attacking in anyhow ionic attacking and taking the proton is a very fast reaction. So, step only delayed on the first step only. In the first step, rate depends on only on the alkyl halide, but not on the OH constant. Therefore, it is called E1 mechanism. 1 stands for what? Unimolecular. What is that molecule? The first that is only alkyl halide concentration alone deciding the rate. That is why we call unimolecular elimination. When this reaction takes place means preferably the alkyl halide should be on the 3-degree type, and however the base also should be strong enough. When OH is attacking and then this so the backside attacking OH is not taking place because of the steric hindrance. First Cl will go out, then a carbocation followed by this. So, it passes through one important feature, that is carbocation. Whenever the carbocation is formed, the reactions will take place some rearrangements also, if possible only. However, if there is no possibility, then let us take ethyl chloride, you will get a carbocation, then no chance of undergoing rearrangement. But if there is a chance of rearrangement, that means the so formed intermediate, if it is 1 degree or 2 degree, there is a chance of becoming into 2 degree or 3 degree, then that undergoes this type of the elimination. That is intermediate. Already this is an intermediate, it changes into another intermediate and then becomes into the product formation. So, such a type of eliminations also may be taking place. An example, let us see. So, another feature is rearrangements may also involved. Rearrangements may be involved, especially in which type of mechanism? In the E1 mechanism. In E1 mechanism, rearrangements may involve. For example, if the compound is one side you have a tertiary butyl, one side you have a simple CH3, a Cl is there, okay, right. This type of compound, if the ordinary elimination takes place like this is called E2 elimination, then the H and Cl will be simultaneously go out and you will get the compound like this. There is no chance of any intermediate for, in the E2 there is no intermediate, directly elimination may takes place. But if the same compound, if it undergoes a E1 type of elimination, in the E1 elimination step 1 what is happening? First undergoing the removal of Cl minus. So, therefore, Cl is gone out. You got a carbocation which is a 2-degree carbocation, right. A Cl goes out, a 2-degree carbocation is formed. Now, we have a chance of promotion for this 2 degree by shifting this CH3 onto this carbocation. So, naturally when there is a chance is there, so carbocation will be rearranged to get this type of this. So, 1 methyl will go that side now. So, you will get a carbocation of 3-degree carbocation. This is called a upgradation. So, whenever carbocation has more alkyl groups, more inductive effect and more hyperconjugation chances are there. So, therefore, naturally 2 degree changes into 3 degree. This step is called a rearrangement step, I call. Okay, right. So, rearrangements may be involved when there is a chance of upgradation of lower degree into the upper degree, 2 degree to 3 degree. Now, this may undergo elimination. So, let us take elimination means you have a beta hydrogen this side, this is identical, but this is different. So, either of this hydrogen may be removed. So, you will get 2 types of the alkenes. One may be like this side double bond, or you may get the double bond that side. Now, this follows a Sergev rule. What is that rule says is from the less hydrogen side, this side we have 3 hydrogen, that side only 1. So, that hydrogen will go, or otherwise you apply. This is dialkyl alkene, this is tetraalkyl alkene, or you can apply the concept of hyperconjugation. 3 plus 1, that is 4 hyperconjugations are there for this compound, right. So, how many here? 12 hydrogen, 12 hyperconjugable, almost 3 times we have. So, 1:3 ratio you will get it naturally. So, 12 hyperconjugable hydrogen stabilizes the alkene more extent, therefore, the second compound the major product will be formed. You can calculate the percentages also based on the hyperconjugable hydrogens availability. So, now in this if this particular compound, for example, ask directly question, this gives this major product 2,3-dimethyl 2-butene. Is it a E1 or E2 mechanism? Means one can easily identify. Unless rearrangement, you can't get this type of, see here neo type of structure is there, here is iso type of structure is there. To get that internal core structure difference, rearrangement must be involved. So, therefore, one can guess, so it is coming through the rearrangement, that means carbocation is involved, that means E1 mechanism is involved. Actually, it has a chance of undergoing E2 also, but if this becomes into a carbocation, we have a chance of upgradation. Therefore, naturally this type of system will undergo E1 mechanism and gives that more. Here, if this product is formed, there is no hyperconjugation. In fact, see, there is one alkyl is there, but hyperconjugations are nil. So, 0 hyperconjugation. Naturally, when compare the stability of that and this versus this is highly less stable. So, therefore, always a stable product formation will be the driving force many times. So, major product that is the maximum hyperconjugations, in fact 12 hyperconjugations are there. So, naturally this compound when you do with alcoholic KOH, you get that 12 hyperconjugable containing 2-butene will be the major product. This is also one of the criteria of the elimination reaction. Similar to this dehydrohalogenation, a mechanism of minus of H2O slightly differs. This is called dehydration. Dehydration is not just similar to the dehydrohalogenation, a slight variation is there. An example, if alcohol I am going to remove, as we have agreed already, the OH will not prefer this hydrogen, but prefers this hydrogen. This is called what? Selecting a beta hydrogen according to the first rule. The OH and the H goes out from the side by carbons, or from beta carbon it is goes out, not from the alpha carbon. So, now the mechanism finally what comes is a double bond is formed. So, beta hydrogen and the OH is going out. But this reaction is catalyzed by the concentrated sulfuric acid and the temperature around 170 degrees centigrade. Now, what exactly the role of sulfuric acid here means? The HOH directly is not going. Sulfuric acid proton is going to attack on the lone pair of this OH. So, this is called what? Step 1. So, mechanism will write this side. So, that is H plus attack is called a proton attack, therefore, you can say protonation. Where from that proton has come? From sulfuric acid. sulfuric acid proton will attack on the OH of the alcohol. So, the alcohol will become now O with 2 hydrogens. One is original one, the other one is also added. You get only one lone pair. Actually, 2 pairs are there. One lone pair will be there, but the other side pair is missing. So, oxygen will get a positive charge. Then consequently, now what happens, the oxygen with plus is called oxonium ion. So, this oxygen will take the pair of electrons and withdraw as a H2O molecule. The whole, that is the bond, from the bond to electrons are withdrawn, H2O molecule will be removed, minus of H2O. That means it is not this HOH is going, but the proton of the sulfuric acid and OH is gone as a water. So, water is removed. So, this carbon will become now alpha carbon will become a carbocation. The rest will be almost the same now. Now, from the beta hydrogen is lost, the 2 electrons will come here, make a double bond. So, therefore, an alkene is formed. The only the difference, exactly the role is of the sulfuric acid also. The proton of sulfuric acid is attacking on OH and removed as a water. This proton is removed and it goes into what? This proton is removed, isn't it? This proton goes into the sulfuric acid. So, sulfuric acid gives a proton, that proton OH goes as water, and from the compound that beta hydrogen is removed, that is adjusted against the sulfuric acid. So, sulfuric acid donates a proton initially and takes back at the end of the reaction. So, ordinary, as the sulfuric acid concentration is more, the reaction taking place more, that shows the involvement of the proton. You have one more support also. Whenever the alcohol, if you are heating not with sulfuric acid, but you have a sulfuric acid wherein hydrogens are not there, but instead deuteriums are there. This is called heavy, just like heavy water, you can say heavy sulfuric acid or deuterated sulfuric acid. So, originally what should be the answer means the HOH should be the water, will be the one byproduct, double bond is, double bond comes here also, but the byproduct is not water, the D and OH forms HDO, right. H2O will be the byproduct, and the hydrogen which is detached from here goes with sulfuric acid. So, after that sulfuric acid will become HDSO4. The exchange of D with this water and the due to SO4 is after the reaction becoming HDSO4 clearly shows the involvement of the hydrogen atom or deuterium from sulfuric acid, and that is attacking on the OH and going as a HDO, passing through carbocation. Even in this case also the carbocation formation is taken grant or taken as a proof evidence because it is carbocation, it involves the rearrangements and it also undergoes a ring expansions or rearrangements, sometimes maybe ring expansions also taking place. Some interesting reactions will be taking place, 1 or 2 such examples let me quote. For example, if a compound like a cyclopentane containing 1 CH2OH, okay, then this is treated with the concentrated sulfuric acid and heated at 170 degrees centigrade. As usually what happens is what we expect is there is one hydrogen, so this H and the OH may be removed in a normal way and a double bond should be constructed. So, therefore, a double bond containing this type of alkene is expected product, right. But instead of this expected, we get the another product as a major product. This will be coming as a small product only. What happens, the mechanism shows like this. So, first sulfuric acid proton is going to attack on the lone, this OH. So, what you will get is a protonated, the alcohol will come, the O and one more proton. So, a charge. So, this will be dropped now. So, what you will get, this carbon will become a carbocation, right. So, let me write now is separately the carbon containing 2 hydrogens, but there is a positive charge. What is the degree of this carbon? It's a 1 degree. 1 degree carbocations are not that stable, isn't it? So, we have a chance of actually one hydrogen may jump here, so that 3 degree carbocation is formed. But instead of 3 degree, the major of the compound, what is happening, instead of hydrogen cutting and jumping, the carbon with 2 electrons taking and jumping, this will jump here. So, therefore, a direct bond is formed here, carbocation is formed on the junction, carbon will become into a carbocation. But this carbon directly makes a bond with this carbon. So, we have already 2 hydrogens, so the tetravalence is completed. Here, however, a carbocation is formed. Okay. This you can as well write, it is nothing but the 6 carbon system containing a carbocation. Nothing but, both are nothing but same, only thing is it is unusual shape is there, that's all. So, this is nothing but this one. So, a cyclohexane with a carbocation is formed. Now, what happens, side by either left side or right side, it is identical. So, one of the hydrogen will be dropped and the 2 electrons are given. So, we get some unusual product, that is what a cyclohexene. This is what cyclohexene. Now, here what is the help you have or the favorable factor that you have during this particular the second product formation as a major product going into this? Why you get this one as a means? One is this 1 degree carbocation formed has become into 2 degree carbocation. This is right now 2 degree carbocation. Another favor is we have a 5-membered ring, isn't it? 5-membered ring has become into the 6-membered ring. So, when the stereochemistry or the stability of the cycloalkanes are concerned, the cyclohexane has got a better stereochemistry or better stability. So, therefore, 5 to 6 is said to be a promotion of the stability. So, therefore, always 5-membered rings would like to become into the 6-membered if chance is given. So, we are getting 2 promotions. One is 1 degree carbocation has become into 2 degree, this is one promotion. Another one is 5 degree 5-membered ring has become into 6-membered, right. This is called ring expansion, isn't it? Especially it is called a rearrangement called Demjanov ring expansion. Is a Demjanov rearrangement, you can say otherwise. What is Demjanov rearrangement? In this rearrangement, the smaller links like 3-membered ring will become into 4-membered, and a simple example you too can quote like this CH2OH, when I try to dehydrate you will get cyclobutane. When a cyclobutane with OH, a CH2OH, 1 carbon should be there outside, isn't it? So, a 4-membered ring with CH2OH, when I dehydrate it, you will get a 5-membered, a double bond. So, these 2 examples also come under this category. First, you must have a knowledge of the dehydration goes through the carbocation, and then that carbocation has a migrating or expansion capacity. So, therefore, this type of the unusual the ring expansion is taking place is known as what? Demjanov ring expansion. This is one sample example, right.